What's up, crustaceans? Hopefully, you guys don't have to listen to my dogs bark today. But if they do, my bad. Sorry, didn't mean nothing by it. So we are going to talk about displacement and velocity again today. But today we're going to really focus on graphs and how we can get different graphs of the two different variables from different problems and how the two graphs relate to each other. So there's going to be some super important information here. Memorize it for the rest of your life. I want you on your deathbed to be whispering to your grandkid. They're going to be like, "Grandma, please don't leave me. Please, Grandma, I'm going to miss your homemade bread." And then you're going to be like, V versus T. X is the area underneath. And then you're going to fade away into nothing. And it's going to be so sweet. And they're going to be like, "No, Grandma, what does that mean?" And you're going to be like, "Physics, boy." So we are going to look at these two graphs today. We're going to look at what do all the parts of the graph mean. And when I say parts, I mean the intercepts, the slopes, and then probably something you've never really looked at on a graph before. But we're going to talk about the area beneath a graph. Someday, when you guys are all grown up and you leave the nest, you're going to take calculus and you're going to learn this sweet thing called an integral. That's a fancy word for the area underneath a graph. And we're going to talk about that today. So let's dive into it. We don't need any vocab today. We're just going to go straight into examples. So hopefully this is a little bit shorter than normal. So we're going to go ahead and look at, I was going to call these one-dimensional graphs, but my pen's all goofed. Hold on. I apologize. Let me get this all set up. There we go. Okay. I was going to call these one-dimensional graphs, but I realized that sometimes I need like an extra half a dimension just to make sure that we can read the graph clearly. So I'm going to call them 1.5 dimensional graphs of position. Another name for these I've heard is a motion map, but this is a good way to represent what's happening in a problem. And it's going to teach us some important stuff about the spacing between an object when it's moving at a constant velocity. So let's read this question. It says, Mr. Barton walks forward at 2 meters per second for 4 seconds, stops for 2 seconds, then walks backwards at 1 meter per second for 3 seconds. So let me grab a ruler really quick. I maybe should have done this ahead of time, but hindsight's 20/20. Let's stretch this bad chicken out. And dang, this thing's maybe not going to be long enough. Let's stretch it out a little more. There we go. And we'll go ahead and mark this thing off. You want it to be, I think, at least 9 long. So let's go ahead and do 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, cool. There we go. Got our one-dimensional graph labeled. All you need is a straight line. You don't need the y-axis today, for this graph anyway. All right, so each one of these is going to be 1 meter. This is the displacement axis, so we'll put a little x in meters. Okay. So it says Mr. Barton walks forward at 2 meters per second for 4 seconds. So let's talk about that first. I'm going to start here at 0. That's my first point. Actually, let me do it. Let me raise it up a little bit, and we'll actually do like a little circle. So there's Mr. Barton. That's top of my head. Perfectly spherical. So if we're walking at 2 meters per second, let's break that down. 2 meters per second. What that means is 2 meters every second. Okay. So we're going to do that for 4 seconds. So 1 second passes, I go 1, 2 meters. The idea of a one-dimensional graph or a motion map is that it's kind of like you have a camera set to take a picture once every second, and you draw what the camera captures. So we start at 0 seconds, we take a picture. 1 second passes, we take a picture. Another second passes, we go another 2 meters, right? 2 meters per second. Another second. So that's 1, 2, 3, 4 seconds. So these circles would be our motion map. Then it says for 2 seconds, Mr. Barton stops. This is why I need the half dimension. If I were going to just take a picture again, it would go 1, 2, and they just overlap. But then it's hard to tell how many seconds we've been stopped for. So what I tend to do is I like go into another axis. Oh, that's all one thing, huh? So there's 1 second of stopped. There's 2 seconds of stopped. Okay. Then walks backward at 1 meter per second. So we're going to go backwards. This we could say is -1 meters per second. If we want to put a negative, that would indicate go in the negative direction. So we're saying this way is positive, that way is negative. So we're going to go back 1 meter, a second happens. Back another meter, a second happens. Back another meter, a second happens. So these are our positions after every single second. We could very easily transform this into a regular 2-dimensional graph with displacement on the y-axis and then time on the x-axis, right? We could go, okay, start at 0, 1 second, we go up to 2. Another 2, go up 2. 2, 2, pause, pause, down 1, down 1, down 1. But there we go. So these are motion maps. Sometimes these are handy to visualize things, and they help us look at spacing between stuff. Sometimes looking at a graph like this isn't, I don't know, something in your brain just doesn't quite click the same way it does this way. So it's nice to have different ways to visualize things. All right, so that's one way we can represent the motion. Disclaimer, this is not really on the AP test, but I think looking at it a second way just will help us understand what we're doing a little bit better. Okay, let's look at how you'll probably see it on the AP test as an XY axis with displacement on the y-axis, time on the x-axis. And then we're also going to look at a velocity versus time graph. And we're looking at the exact same situation we just looked at. So I'm going to walk forwards at 2 meters per second for 4 seconds, stop for 2 seconds, then walk backwards at 1 meter per second for 3 seconds. So let's go ahead and do our displacement graph first, since that's really what this motion map is trying to represent. It's taking pictures of our motion and our position or our distance away from where we started. So we start at 0. 1 second passes, I go 2 meters. So we're going to have that chunk. Another second passes, I'm already at 2 meters, so I need to go 2 more meters. So we'll be right there. Oh no, this is not anywhere close to tall enough. Let's back up a little bit. If you'll allow me. Now it's tall enough. All right. So 1 second, we go up 1, 2. Another second, we go up 1, 2. 1, 2. And then 1, 2. All right. Then we stop for 2 seconds. So for 2 seconds, we're stopped. That means we're going to maintain the same position. There's our 2 seconds. And then we're going to walk backwards. So we're going to get closer to the origin. 1 meter every second for 3 seconds. So we'll go 1, 2, 3. Okay. All right. Now let's go ahead and look at our velocity graph, and we can figure it out from here. So let's ask ourselves, what is our velocity at the start? Well, it says I'm walking forward at 2 meters per second. So we're going to go up to 2. At 0 seconds, we'll say I'm already moving. I'm going 2 meters per second. 1 second passes. How fast am I walking? I'm still going the 2 meters per second. So it's going to stay at 2. Another second passes. I'm still at 2 meters per second. So 2, 3, 4. And we get a horizontal line. This means constant velocity. Whoops, I got my letters backwards there. Okay. If we have a horizontal of anything, it means constant. So here would be constant displacement. This would be constant velocity. Then it says I'm going to stop for 2 seconds. If I am stopped, how fast am I going? Think about it. Chew on that. 0 meters per second, right? I'm going 0. I'm not moving. So every second, I'm moving 0 meters. So this will drop down. You should not draw a line connecting this. If it makes you feel real uncomfortable, I believe the AP test doesn't really care if you put a dashed line just to show that they line up. So we're going to go 0 meters per second for 2 seconds. And that says we're going to walk backwards 1 meter per second for 3 seconds. Backwards, the way we represent a vector as being backwards or going the opposite direction is we change the sign. So this would be -1 meters per second. So we're going to go down to 1, and we're going to go for 3 seconds. 1, 2, 3. Okay, let's look at a couple of things here. Let's ask ourselves, what is the slope of this section? Well, slope is just rise over run. So I went up 2, and I went over 1. Oh, my slope is 2? Wait, my velocity is 2. Oh, okay. So the slope, write this down. This is another one of those things you need to remember for the rest of your life. Let me put it in some place that's not quite so hard to read. Slope. Hold on, how do you spell? Slope of displacement versus time graphs equals velocity. So we have a slope of 2 right here. That means we have a velocity of 2. Right here, we're rising 0, running some. So 0 divided by any number is 0. Slope is 0. Velocity is 0. Here, we're going down 1 over 1. So down would be negative in the y direction. Right 1. That's a -1 slope. What's the value of our velocity here? We are lined up with -1. So whatever your slope of a displacement graph is, that is the value of your velocity. Okay, cool. That's pretty tight. You're going to need to remember this fact for the rest of your life. Yeah, right? This also kind of lends itself to the idea that velocity is the rate of change of displacement. Okay. And we know this because of our displacement equation. Oh, sorry, that should be a plus. Man, you guys, I'm just losing it today. It's been a long day at work, I'll tell you what. If you guys don't have mind, let me take a couple minutes to tell you about... No, I'm just kidding. I'll talk to my therapist later, but I'm just kidding. Not that there's anything wrong with me. Anyway, I digress is what I'm trying to tell you. So if we rewrite this, I tend to have this formula memorized. The way I usually think about it is this. You can write it either way. They're the same because addition is commutative, so the order doesn't matter. I like to write it this way because then it really lends itself to the y equals mx plus b format. And then that really solidifies in my brain that velocity is the rate of change. And if I want to find velocity, I'm looking for the slope of a displacement versus time graph. Cool. So that's what we're trying to look for here. Now, let's go the opposite direction. We're going to have the velocity, and instead of making the displacement graph first, let's just only make velocity, and then we'll try and find displacement, and we'll look at some cool tricks. So it says a mass is moving at a constant of 3 meters per second for 3 seconds. So we'll go up here to 3, and we're going to go 1, 2, 3. So we're going to go to there. Okay, it's constant, so we should have a nice horizontal line to show it's constant. Then it's going to slow down to 1.5 meters per second for 2 seconds. So we'll go 1.5. We'll go 1, 2. And -5 meters per second for 5 seconds. Dang, I didn't make my graph big enough. Let's extend that out a little bit. Let's unlock it. Extend that out a little bit. Get our ruler. Rotate that bad boy. And we'll just make sure that we have enough room. Perfect. Okay, so we're going to go down here to -5. 1, 2, 3, 4, 5. Come over here. And we're going to go horizontally for 5 seconds. So 1, 2, 3, 4, 5. And here's our graph. We can put these little dashed lines just so we know everything lines up. Okay. So let's talk about one way we can find the displacement from a velocity graph. We could go through all the trouble of finding our displacement graph. We could go ahead and draw this. We go, all right, I need a slope of 3 for 3 seconds. Then I need a slope of 1.5 for 2 seconds. So it kind of just bends there. And then I need to go -5. And then we could do it that way. However, there's an easier trick that we can use to find our displacement that you're going to want to be aware of because it comes up later and it's pretty useful in general. So another way that we can find the displacement of an object is by looking at the area under a velocity graph. So this is a pretty straightforward example because if we look at our areas, let's break it up into 3 chunks. We'll look at under this one, and then when we say area under, we mean area between the graph and the time axis. So this first chunk right here, we're going to want to find this area right there. Then we're going to need to find the area of this. And then lastly, we're going to find the area of this right here. All right, doesn't need to be perfect shading, but you know. All right. So if we look at these 3 areas, these are super nice shape for finding area. These are rectangles. And we all know that the equation for the area of a rectangle is base times height, alternatively length times width, however you want to say it. It's the long edge multiplied by the other edge. I shouldn't say long. This one's a square, but you know. So we're just going to find the area of these little squares or rectangles. So 3 times 3. The area of this one is 9. This one is 2 wide and 1.5 tall. So 2 times 1.5 is 3. And then this one is -5 and 5 wide. So -5 times 5. This one is going to be -25. And it's important that we say anything underneath the time axis is negative because we're moving backwards, right? We're going in the negative direction, so we're losing displacement. If I walk back towards the origin, then I'm going to get closer to the origin, right? So it makes sense that we're losing distance from the origin or displacement. So during this time, if I'm going 3 meters per second for 3 seconds, I go 9 meters. If I go 1.5 meters per second for 2 seconds, I'll go 1.5. then another 1.5. So I go 3 meters. And then I go back 5 meters per second for 5 seconds. So I go back 25. So we just add these three numbers together. So 9 plus 3 plus negative 25. 12 minus 25. We're going to go a total of negative 13 meters. Cool. Awesome. Let's talk about one more thing. Let's just check the units to make sure that I'm not lying to you and that this isn't just some kind of wizardry, warlockery that, teachers like to say. So you can verify this. This axis is meters per second. So this height is 3 meters per second. This width here is time in seconds. This is 3 seconds. If we take 3 meters per second times 3 seconds, and we multiply these, 3 times 3 is 9. The seconds on the bottom cancels the seconds, and our units are in meters. Wow, isn't that a coincidence? That's so cool. I love physics, you guys. It's so tight. So even our units work out. I'm not lying to you, I hope. So if we look at the area between the graph and the time axis, then we will get our displacement. An important note that we should make here. This process cannot tell you, let's write this down, area of a V versus T graph equals change in position or displacement. It cannot tell you X initial. So if I say we're going 3 meters per second for 3 seconds, that tells me that we're going to go 9 seconds. In no way does that tell me where we started from or where we end up. All it tells me is that during these 3 seconds, I have gone 9 meters. So it tells us displacement. It does not carry any information about your starting position, though. Cool. Let's do a hard problem. So this is the same setup, velocity, time. I had the foresight to make this graph ahead of time. So it says a mass is moving at 3 meters per second initially and continuously, that means nice smooth graph, increases its, there shouldn't be an apostrophe there because it's possessive, speed to 13 meters per second over 5 seconds of time. So 1, 2, 3, 4, 5 seconds here. We're going to go from 3 meters per second all the way up to 13 meters per second. And I counted these. You can trust me, but you can recount them if you feel like it. So you're going to say, all right, how the heck do I find the area of this thing? Okay. Just so you're aware, the area of this shape, let's talk about what this shape is first. This shape is a trapezoid. Ooh, that's an ugly trapezoid. Let's make it a nicer trapezoid. There you go, nicer trapezoid. Okay. There is an area formula for trapezoids. This is base 1, this is base 2. The area is height times base 1 plus base 2 over 2, or the average of these two. Basically what this formula does is it cuts off this and glues it on right here and turns it into a rectangle. But, okay, I don't expect you to memorize this. I just have it memorized because I'm a math teacher. Okay, let's talk about an easier problem-solving approach that we can take to finding the area of this thing without hurting ourselves or having you remember obscure shape area formulas. So this, we want to find the area of this whole thing. Let's go ahead and cut it up. Let's make a horizontal line at this intercept right here. And look at that. Now this thing is a rectangle. And then this thing here is a triangle. And we definitely, I really hope you guys know the area for both of those. If you don't let me make you feel bad. I understand that everything takes up space in your brain, and maybe you don't have space for those formulas. But these are ones that I kind of think you should know. So let's go ahead and find the area of these two shapes, and then we'll just add them together, and then that'll give us our total displacement. Another thing that I think is really handy is let's take a, never mind, we'll talk about it at the end. Okay, let's find some areas. The width of this thing is 5. So this width from here to here, that's 5. This height, here's 13, here's 3. So this length here is 10. So the area of this triangle is going to be 1/2 the base of 5 times the height of 10. So we'll do 1/2 times 10 is 5 times 5. The area of that triangle is 25. Okay. Then if we look at the pink portion, the height here is 3. The width is still 5. So base times height, 3 times 5. That's 15. And then we add our two displacements together. And we're going to go a total of 40 meters as our car or mass speeds up from 3 meters per second to 13 meters per second over 5 seconds. So that's how we're going to find some displacements. Should be fun. Now, as I was saying, this problem you cannot solve with your displacement formula. And let's talk about why really quickly. Your final position or your final displacement equals your initial velocity times time plus your initial displacement. There's kind of like a star asterisk here, and then the footnote says only for constant velocities. Okay. If you plug in your initial velocity here, if you plug in initial velocity of 3 times the time that we're traveling for, 5, that's 15, and then we don't even know what our initial displacement is. You only get this chunk right here. What you're finding with this is this little piece here. So this formula is somehow ignoring that triangle on the top. We are going to learn how to put this triangle on in a later video. We're going to have to amend our formula, but just be aware that as it stands right now, this formula is not powerful enough and hasn't eaten enough Wheaties to be able to solve this problem. So this finding area method allows you to solve some trickier problems without having to use trickier formulas. So it's a powerful tool that you kind of want to keep in your arsenal. All right, so that's what you're supposed to learn today. If you have any questions, keep that stuff. No, I'm just kidding. Don't keep it to yourself. Go tell me about it. Go hop in the WebEx. Say, hey, Mr. Barton, you mumbled a lot. I think I heard your dog walking around. My sister smells funny. My brother was breathing in my ear the whole time, asking me if it was his turn to play the PlayStation. I just can't get any peace and quiet around here, Mr. Barton. I've got some questions. Go tell me about them in the WebEx. Until next time, you guys take care.